radiocarbon is so low. This shows a mass scan normalized to carbon-12 abundance. And so this is what would come out of an ion source in one of these accelerators, or it would come out of an ion source in a mass spectrometer if you want to use that. So you get a lot of mass 13 and mass 14 molecular ions. Your mass 14 for modern carbon is 12 orders of magnitude down. And we really want to go down about 3 orders of magnitude below that for old samples. So you're down 10 to the minus 15th. You've got to eliminate all these other species to the 10 to the minus 15th level. And it's just not possible to do that with a mass spectrometer. So what's used are nuclear physics techniques. I want to briefly mention the sample preparation. There's some mechanical and chemical pretreatment. And then the sample has to be converted to CO2. And then that CO2 is reduced to graphite. The graphite is then put into a sample holder, and that's put into the accelerator. This is an example of how the sample is converted to graphite. I won't go through all the details, but I can give you the references later. Basically, it's done in a sealed tube with a heater and a cold trap on the other side, and the CO2 and hydrogen in the presence of a catalyst converts to graphite and water. And this is a picture of some of the graphitization lines at the University of Arizona. It's a bunch of glassware and stainless steel tubing. This is a diagram of one of the particle accelerators that's used. This was our accelerator at Livermore. The sample is put into an ion source. That's run through the accelerator, and you have to go through a magnetic band and some sort of electric separation to get into the to separate out all of the interfering species. Here is a photo of our accelerator at Livermore. So this is an old nuclear physics accelerator. Many universities have these. This is called an FN tandem. There's one at Purdue. There's a number of universities have the same machine. And these were sort of recommissioned to use as radiocarbon dating machines when this AMS technique started. Nowadays, there's also some special purpose accelerators that are smaller that are being used. So this is the one in University of Toronto. Contamination and background are issues. There's samples can be contaminated in situ. There's not much you can do about that in the lab. There's a background that you get from processing, a background from the instrument itself. But all of these can be characterized and corrected for by processing blanks in parallel with your unknown. If you know the blank has no radiocarbon, it can be used as a process blank to subtract out the background levels. What got me looking into this again and recently was the RATE project from Institute for Creation Research. They had claimed a lot of problems with this technique and said that radiocarbon doesn't work. That basically they said that what people are seeing and calling contamination background are really intrinsic radiocarbon left over from the creation. And there's a number of problems with that. I've written up a detailed analysis of their claims and what the problems are, which is on the ASA website, and I also have some copies here if anybody wants it. But I don't have time to go through the details right now. I want to just briefly mention some of the modern capabilities and some of the things that can be done with radiocarbon. As I mentioned, sample size is about 1 milligram. The dates, you can go back 12,000 years with tree rings. You can go back as much as 75,000 years with some isotopic enrichment techniques. And you can get about a plus or minus 20-year error on your uncalibrated date. Number of applications for radiocarbon. Archaeology is the main one, or the first one, but now some of these other applications have become important. The Dead Sea Scrolls, these were dated in 92, and the radiocarbon dates are the blue lines. The paleographic dates based on handwriting, letter styles, are the red boxes. And there's quite good agreement. The radiocarbon dates tend to be slightly older, but that could be real because some of these things were reused. Some of them were, the material was made before the writing. The Shroud of Turin was a famous thing that was dated. 3 different laboratories dated 3 different samples, got very consistent numbers with an age of 1260 to 1390 AD after calibration. And a lot of people don't like this because they want to believe this really was the Shroud of Jesus. About the only way to argue against this date is to say that the samples they measured were not from the real shroud, but were from repairs made to the shroud. I don't think that's true. I think they were very careful in selecting their samples. Geoscience, there's a lot of applications. This is ocean circulation, as we saw yesterday from Keith Miller. The ocean waters have been dated by radiocarbon at 3 kilometers and at 0 kilometers, and you look at the difference, you can see the residence time in the ocean and deduce the ocean circulation. Climatology, a lot of things have been done. Carbon cycle research is a big field right now. And in bioscience, there's a number of things that have been done. A lot of new things are possible in bioscience that weren't possible before because of the sample size. So in summary, radiocarbon has been calibrated about 45,000 years with the Lake Varves. This new technique of AMS allows very small samples, and there's lots of interesting applications that can be done with it. Okay, that's a good question. I'll try to be quick here.
What was his question?
Yeah, the question is, what is it about the accelerator that allows the better discrimination? First of all, this is a tandem accelerator. Negative ions are injected into the machine. They are stripped at a terminal in the center of the accelerator. So you go in with carbon -1. You strip it to carbon +3 typically. And that stripping process kills all of the molecular ions. They don't survive it. So what comes out are just atomic species. And then those atomic species are bent through a couple of stages of mass selection and then a stage of energy selection or velocity selection. And then, so that gets rid of most of the other stuff. And then the final step of separation is the detector itself, which uses nuclear physics techniques of energy loss in a gas counter cell. So this is a gas-filled detector typically, and as the species go in, they lose energy proportional to Z. Their range is proportional to Z, and so that's what helps give the discrimination.